All right, here we go. 16.2, polar equations. We're going to take rectangular, turn it into polar, polar, turn it into rectangular. It's going to be awesome. Are you ready?
Yeah.
You might have made a cameo on here. Way to go, Maddie. Okay, these are items we already know. This is kind of like an identity list that you want to be aware of. Okay, I would just get familiar with that. Okay, it's just right triangle trig. That's all it is. Okay, now I want to solve for x and y, and it's going to be another set of identities that I can use and put in the toolbox for when I change from rectangular to polar or the other way around. Okay. So let's talk trig for a moment. If I look at this triangle, would you agree that the cosine of theta equals x over r? Yeah. In the unit circle, we said cosine is x. Yeah, that's because r was what? 1. So in a triangle where r is something other than 1, what is x equal to? R times cosine of theta. So with that logic in mind, how would we write a separate equation using sine? Sine of theta equals what? Y over r. Therefore, what does y equal? R sine of theta. Okay, that's nothing groundbreaking. That's where we've been. We've just been dealing with the unit circle where r is 1. So we said x equals cosine, y equals sine. Good, cool. Okay, we're going to use these items, all 6 of these, in some way, shape, or form, to take an equation of, say, a line and write it in polar form. Okay. These are some problems here that I would suggest working on. I think maybe I'll do one of them right now. Would somebody like to see one in particular where we take a polar coordinate and turn it into rectangular form? Number 2, sure. Whenever I see a pi over 4, I know that the x and the y are going to be equal. Maybe one's positive, one's negative, but they'll have the same value, right? Because it's a 45, 45, 90. But this would end up where? Which quadrant? Ooh. So I'm going to extend which way? Left 3, 1, 2, 3, and rotate clockwise or counter? Counter. So I'm going to rotate to here. Okay, if I were to look at this triangle would look like such. I know I'll have a negative. Some of you may recognize that when you have the hypotenuse of a 45, 45, 90, I do this. Some of you may not. Another form of that, a varsity form, would be negative 3 root 2 over 2. Negative 3 root 2 over 2. Are you with me? What if you didn't recognize that? Well, what if you know unit circle values? Okay, so I know that in the unit circle, in the third quadrant, if I have, let's say, a hypotenuse of 1, that would make this negative root 2 over 2 and negative root 2 over 2. Well, how much do I have to multiply 1 by to get 3? 3. Doesn't that give me negative 3 root 2 over 2 and negative 3 root 2 over 2? Yes, it does. So the coordinates of this point in rectangular form are left negative 3 root 2 over 2 and down negative 3 root 2 over 2. Anytime you see a pi over 4, a 7 pi over 4, anything over 4, think it's going to be the same, maybe negative positive, but it depends on what quadrant. This would be rectangular form, where polar form was, what was it, negative 3 comma pi over 4. So what's cool about this, you guys, is that I can find an extension rotation that matches the left down point. So that means I can write an equation for any linear or for any function, rectangular function in terms of y and x, in terms of r and theta, and match it. Like match every single point on the curve or the line. It's pretty cool. Let's try one on the next page. So let's look at B first here. Can we all agree in rectangular form that if I drew a picture of y equals negative x, that's what it would look like? You okay with that? Decent? Yeah? Okay. On the previous page, what did we say y equaled? R times what? Sine theta, and x equaled r cosine theta. I'm going to do a direct substitution here. If y equals r sine theta, and x equals r cosine theta, well, what the heck? This is weird. Oh, watch this. What do we know about tangent theta? It equals 4 y over x. So we like things in terms of tangents. Do you see a way to turn that into tangent? Divide by what? Divide by r cosine theta. There's a strategic step involved here that you may not see, but that I want to get rid of r. I'm going to get rid of r altogether. I don't always want to do that, but in this case I will. What will I get on the right side? Negative 1. What do I get on the left side? Tangent theta. Okay, where is the tangent of theta equal to negative 1? Which quadrants? 2 and 4. Oh, where's this line? 2 and 4. Okay, so does it matter what r is here? Is r at all involved in this formula right here? No. So r could be anything. Well, okay. What values of theta give me a tangent of negative 1? What are my two answers to that? How about not pi over 4? That's positive 1. 3 pi over 4 or 7 pi over 4. We could also call that negative pi over 4 if we wanted. So let's pick an r value. I don't care what it is. Somebody pick a positive number.
3.
3. Okay, ready? Here we go. 1, 2, 3. Rotate. Ready? Rotate 3 pi over 4. I'm on that line. Somebody pick a different number. Pick a negative one, Grant. Negative number. Negative 7. Thanks for making that go outside of the bounds of my... That's fine. Okay, that's negative 7. And then how far do you want to rotate? 7 pi over 4 or 3 pi over 4? Thank you. That was just great. Oh, guess what? It would hit the extension of that line at some point. It's pretty cool. I can write a polar function that will land on that rectangular function every single time. But there's no r involved because it doesn't matter what r is. Right? Okay, let's look at another one here. I want to look at part C. This one's really cool. What does y equals x squared look like? A parabola. Wait, I can draw a polar function that looks like a parabola? Yep. Oh, that was bad. Wow. Thank you for that. I appreciate that. Delivering positive messages every day. That's y equals x squared. I'm going to come up with a polar function that can match every point on there. I can change theta, and it'll give me an r that will get me to each point on there. Okay, so what does y equal again? R sine theta. And x is r cosine theta squared. Okay, so it takes a little bit of experience to see this coming, but I'm going to leave the left side alone. I know, that's like amazing. Isn't that amazing how good I was at leaving the left side alone? Yeah, okay, thanks. What happens if I square this expression? What do I get? R squared cosine squared theta. It's cosine squared, not cosine 2 theta, right? Okay, so my goal here is I want to get r alone. And experience tells me that it's going to be best if I do this. What will the right side become? The right side. R. Good. I wanted r alone anyways. Good. The left side, if I divide by r cosine squared, what happens to the r's? They're gone. I get this. Prepare yourself. Do you see it? Sine theta over cosine theta times another 1 over cosine theta. I get secant theta tangent theta. Okay, so I want you to take a snapshot of this in your brain for a moment. Pull out your calculator. Secant theta tangent theta. Before you get too far, watch what I'm about to do. Let me pause it, give you a moment. Okay, on your calculator, when we go to polar mode, guess what mode you have to go to? Polar. Press mode. Press mode. All the way down, you'll see function mode right below radian. Make sure you're in radian mode, as well as polar mode. Okay, now press y equals. Once you've got that, press y equals. Now notice that it's no longer y equals, it's r equals. Okay, so I'm going to type in secant theta tangent theta. Don't get too far ahead of me. There's no nice way to write secant theta, so I'm going to put parenthesis 1 divided by what? Cosine theta. Press the variable button. That'll bring up a theta now instead of an x. Okay, I'm going to nest the parentheses, and I'm going to multiply by tangent theta. Nest the parentheses again. Okay, go to window after you've got that. Window. Okay, don't change anything with theta min, theta max. It should be from 0 to 2 pi. Go x min, x max, negative 10 to 10. And go y min, y max, 0 to 10. Okay, and then check out the graph. Check this graph out. That's a parabola. That's a stinking parabola. Isn't that awesome? So two functions can graph that. Here are the two functions. Y equals x squared, and r equals secant theta tangent theta. So your independent variable here is x, and it spits out a y, right? So if I go 1, it spits out a 1. Right? You with me? If I go 2, it spits out a 4. Okay. In the same way, the input for theta gives an output of the radius. So this is going to be kind of funky, but get ready. This is really cool. Right here, we agree that 4 is the output for y, right? Well, 2 and 4, if I take 2 squared and 4 squared, I get the square root of 20. Right? For this radius. Oh gosh, terrible. Dang it. How do I? No, I want to do this. Can I do this? Will it do it? Oh! Okay. Oh! Ah! No! This was so cool. Dang it, Peggy. Okay, basically, what happened here was this. When I plug in this value for theta, I get this value for r out. What happens as I increase the angle? As I make theta larger, r gets larger. As I make theta larger, r gets larger. As I make theta larger, r gets larger. What happens when theta is pi over 2? What happens on the parabola? It goes back to 0. What's secant of pi over 2? What's cosine of pi over 2? 0. It's undefined. It drops right back to the origin. And then it starts with all the angles afterward. So I sketch this, right? Not a well-sketched portion, right? But it does this. And then once that angle hits pi over 2, it flips over to the other side. And I get these, which form the rest of the parabola. It's like, it's a really cool thing, right? All of these lines in here don't matter. All that matters is the points where they align along the parabola. It blows your mind. Once it hits that pi over 2, it just goes, whoop, comes back down to the origin, starts over, and then works its way back down. Okay, let's move out of the calculator and back to one more problem. What just happened? Did I? I did close Smart Notebook. Way to go. Look at that. That's just an aggressive. Okay, here we go. Let's do one more. Let's do a let's go to number 2, part A. Number 2, part A. If you got to go to the dentist, you got 2 minutes to get there. Oh. This right here, you guys, this right here is a circle. What? Does theta have any bearing on what happens to r? No. R is always -3, so 1, 2, 3. Okay, so what if theta was, pi over 6 or pi over 4 or pi over 3 or pi over 2 or 2 pi over 3 or 3 pi over 4 or 5 pi over 6 or pi? What am I building? A circle. Regardless of what theta's value is, r is always -3. Sweet. Sweet. So how do I put this into rectangular form? Well, I got a couple of things that are going to help me. X squared plus y squared equals r squared. So what does that mean r equals? Square root of x squared plus y squared. So wait a minute. I know what r is. What is r? -3. Okay, so plug it back in there. Wait a minute. This is weird. Well, what happens? I'm going to go backwards for a moment. What happens if I square both sides? That's the equation of a circle with a radius of what? 3. Does that ring a bell? Okay, now I'm going to go one more time here for a moment, because this right here, when you get rectangular form, that's not a function. It's built of 2 functions. It's built of 2 functions. So watch this. I kind of worked backwards to show you this. Well, okay, so let's do this. Let's take the square root of both sides, right? Let's take the square root of both sides like we did before. I get... Okay. If I take the square root of both sides, would you agree when I take the square root, I get that? Okay, that gives me 2 separate functions. I get positive x squared plus y squared equals 3. I get negative square root of x squared plus y squared equals 3. Now, we like typing things into our calculator with y equals, right? So you're going to see in a moment here, this is actually pretty cool. I'm going to erase this. I wanted to show you that there, but if I were to solve for y, I would take y squared equals 9 minus x squared. And when I take the square root of that, I get 2 possible answers. The positive version and the negative version. Guess where they show up? There's one of them. And that one would show up right there. Woo! It's pretty cool. All right. If you want to, you can graph that. It's totally up to you. You can trust me. I make like 300,000 a year, so I only make a few mistakes, most of which are on my choices and jokes. But that is taking polar or rectangular into the other form, and then you can graph it. Some of you are very excited. So excited. Well, it's the weekend, and it's not snowing out right now. So just think only about 60 hours, and you'll be right back here doing more work Monday morning. Like, subscribe, comment below. $11 to GNC, not to Aiden, because, well,
Giveaways don't work.
they do.